Okay, so we will start, and my title is a bit long, so I will only say that we will be speaking about practical invasive attacks, but I will try to link this to a threat model, and I was choosing compatible product creation for this because I think it's big enough that it's a decent threat model. So an introduction, I will speak about myself and Texplained for 1 minute. So, by the way, I need to see the time. So I'm Olivier Thomas, so my first name is Olivier, just like to make this sure, you know, it's not like this on the papers for hardware.io. I've been working 8 years in pay TV, and that's where I got exposed to invasive attacks back in the days. After that, I created a company which is called Texplained, and basically we are specialized in IC reverse engineering for a number of different things, from design review, so it's not really reverse engineering, but from design review to digital forensics, security audits, counterfeit check, and this kind of things. The field of application of IC reverse engineering is pretty big. But now I want to concentrate on this because there's not so much public data, so I'm trying to give you public data about this. Secure elements themselves, when I say secure elements, it's secure elements, smart cards, TPM, all the secure chips, you know. They rely still on obfuscation a lot, right? So I want to also discuss this, and to me, the certification schemes are not adapted for evaluating integrated circuits reverse engineering based attacks. So I think it's a good opportunity. There's a number of people that are using those techniques, and it's growing big. You know, like when I started 18 years ago, reverse engineering chips were like something for the mad people, right? But now it's done a lot by the chip vendors themselves for competitor analysis, but also by the digital forensics guy, like the law enforcement agencies are using this to extract evidences from like encrypted products, let's say. And then we have like this compatible product creation that I want to talk about. And the idea is I really want to show, at least to give you a glimpse of what the cloners actually do to basically create some compatible products. This is also applicable to a number of other attacks or hacks, but I will concentrate on this one. So I want to establish the threat model, but I want to demonstrate the technique and raise awareness. Disclaimer, the analysis that I'm going to show you. So first of all, I will not tell you what the chip is, because to be fair, I don't know it. So for me, it's a black box, a piece of epoxy. And the analysis is not done yet, right? But you will see already that the number of steps that I will present is pretty big, you know. And just to say, yeah, invasive attack is still like something that is like time consuming a lot and difficult. But let's see if the threat model justify that we get interested into this. I want to thank also all the team at Texplained, especially the one that were working on this project. So Paris, the CEO, Isabel, Steph, and Evan. So if you are looking at me, hello and thanks. Now let's see the threat model, right? So we focus on compatible products. They are protected brands, not something else than you know, like being able to use like the right printer and the right cartridges. And the cloners, they will basically copy this, you know, in a way. To give you an idea of the problem, the cloners make $5 billion a year, right? So that's pretty big, I would say, and I would even say that one company only is taking 90% of this share, right? So that's pretty big, I would say. And they have like labs. When you will see my lab, you have to consider that this is a very small lab, right? The cloners have like 30 times more machines than I do, and people and so on. So it's not fair competition. They propose compatible products for mainly all of the brands of printer, and they are so big that they can produce their own ASIC, right? So they have one chip that emulates them all, right? So I think it's a very decent activity, and the activity is legal. You can sell the compatible product. So it's just like you can sell it, but to get to the point where you can sell it, you need to basically attack and compromise the original product. So here you see a part of the lab that we have. So it's a very small part where basically you have already enough equipment to be processed the chips. I will speak about this very briefly. But here, what I want to show you is like the guys who are putting chips in their genuine cartridges, right? They don't care about like certification schemes and stuff like this. They know that the threat model implies that the attackers will use invasive techniques, right? So the security measure for those guys is the time that it takes for the cloners to have a compatible product. Okay, and they want this time to be big, of course, and it's difficult, right? Last thing I want to say is the attacks I'm going to show to you. It's a residual threat according to common criteria, because like the time that has been spent, the equipment, and all of this thing is giving us like not so good points, I would say. So without further ado, let's see what this kind of attack looks like, and let's start with the target, right? So the target in printer cartridges, you will find chips that are very close to secure elements. So I put like some pictures of secure elements for those who can recognize things, you know, and those things are packed with countermeasures, and they are supposed to prevent any attack, right? Plus the fact that you don't have like public documentation and this kind of thing, it makes it hard to even know what they are, you know. But inside the printer cartridge, you also have like what's called custom hardware functions, right? So now if you have the firmware of those chips, that's not enough. You will also need a piece of the hardware, right? So it's even more secure than those chips at some point. My targets, right? So I told you before, when I got this target, it's just a piece of epoxy here, right? And I have pins going in, pins going out, sorry. But that's all I know. So when I say I do black box analysis, that's the one. No reference on the package, no reference on the die itself, no die marks, unknown CPU, unknown architecture, black box scenario. Our target is to be able to extract the memory of the device, but also extract the hardware, right? As if you wanted to basically emulate this component. And of course, we started by just looking at the frames between the printer and the cartridge. We did some SPAs that are pretty much useless. We know that if something happens at the beginning when you put the device, good, yeah, it's very useful. And so we decided to do some kind of construction analysis, right? So that's basically doing few steps, going to the silicon to see the transistors, how the chip looks like. And we've been performing a number of like different operations. So we could say at the end of the day that this is our target, finally, right? So the target, by looking at just one picture, you will see that it contains some analog functions, a digital logic part, and then one flash, one ROM, and two RAMs, right? So I think today we will concentrate mainly on the ROM, and you will see that getting ROM out of things like this is like pretty difficult. So you see the strategy that we choose, and I will not comment it here. I think I will go directly to the slides. And the first thing we started is extracting the netlist, right? So we have a digital CPU. We want to know what this is. So the chip has 5 metal layers, right? And the techniques that we've been using to get like to each of the layer is basically CMP, so mechanical polishing, and plasma etching. Right, so sometimes it's called dry etching also. And by using this, we could remove like layer by layer to take pictures with like a scanning electron microscope. So that's the pictures of the layer. So from like I think they have a laser pointer, which is nicer, with like the PCS. So here we see the transistors basically. With this layer, it forms the logic cells, right? And then you have all of the interconnect layers on top, right? I didn't put like the upper layer because you see this, that's only ground and DCC, so not very useful for the guys who reverse engineer the chips. From the pictures, we've been using a software, so it's called ChipJuice. It's been developed by Texplained directly. And with ChipJuice, you can basically select an area of interest for each of your scans, right, in the SCM. So a scan for this chip was about like 15,000 pictures per layer, to give you an idea. And then from this, we extracted the features, tracks, IAs, standard cells, power rails, I mean, you name it, the features that are on the IC. After that, we could use this detection to basically correct the distortion that is introduced by the SEMs, right? The scanning electron microscope, they distort the features a bit. So if you want to stitch them, especially if you have a large number, it's good to be able to distort them back, you know. So, stitching, so that's layer-wise. And then, the most important part is extracting the standard cell library that was used by the designer, right? So you see all the NAND gates, the flip-flops, and all of those things. So you have to reconstruct, the library. So if you do this, then you can go inside the digital circuitry and extract basically where the cells are. So each of the dots here, that's basically a standard cell, right? And that's a very small fraction of the digital circuitry. Alright? This operation is taking a lot of time, you know. So when we were doing this, basically we decided to have a look at the ROM. Okay? So first thing we did was to do a shallow angle polish. So basically we polished across the ROM itself, you know, with a slight angle so we can see all of the layer. Alright? And at some point we can see those things with like short circuits and no short circuits. That's basically your bits, right? So the ROM is an AND. So I can see some attendees of the trainings are like, yes, it's true. So we have an AND ROM here, and we decided to extract the raw binary of the ROM. So basically you scan the bits, right? So you deprocess until you see the bits. You take pictures. From the picture you extract some kind of a grid. From the grid you find the bits. You put everything together. You have what I would call a raw binary, because it's not binary yet, right? Alright, raw binary. If we look at the raw binary, I have something that would look like this. Okay, so that's the bits, basically, as they are stored inside the chip. Alright, so if you see a dot, that's going to be a 0, and if you don't see a dot, that's going to be a 1. Alright? But here you can see that there is a lot of patterns, and there's even like an empty area at the very end of the ROM. Alright? And that is suggesting something which is very uncommon with secure element, that the ROM is not encrypted, basically. Right? So from this stage, we decided, okay, if the ROM is not encrypted, let's convert this raw binary to the proper binary, right? And we tried. We tried pretty hard. So we tried different bit order, for different orders for the bit lines, the word lines, everything that can be used to scramble the ROM data, right? And we got like a few binaries that we could test, you know, and we were looking for strings, no string, right? And we were looking for known opcodes, and guess what? No non-opcodes too, right? So we are at a stage where we think that the ROM is not encrypted, but we cannot make sense of it, right? Because of all of the scrambling and maybe some other things that we didn't see yet. Okay? So next step. So as I was saying, first of all, it's rare to have like secure elements with things with non-encrypted ROMs, right? So the netlist was not ready, so we couldn't use the netlist to verify the encryption and to see if we could do more things. So we were kind of stuck here. So what we decided to do is basically to fully to check first if the ROM was booting. Okay, because if I don't boot on the ROM and I boot on the flash, you know, trying to dump the ROM in the first place might not be the right strategy. Okay, so to do this, we did microprobing, alright? So, and the question is just who's booting the device. So the idea here is we have a chip and we have like, we wanted to probe one bit of the ROM, right? And one bit of the flash and see who starts first. Okay? So simple enough. Problem, there is a shield on top of the chip, and we need to go through it if we want to reach the signals of interest, right? So to do this, what we have been deciding to do is called the local bypass strategy, right? So, first of all, I have a slide about shield, and I know I won't make friends with this slide, but I always ask myself, is a shield a countermeasure against microphobia, right? And if I understand the history correctly, it's not, right? Because long ago, decades ago, you know, to reach the signals of interest, you just scratch the surface of the chip, right? Until you touch the tracks of interest, and bingo, alright? So no FIB modification, there was no shield, it was easy, right? But then you have to see that over time, the sizes of the tracks and all of those things is just like shrinking, over time, and doing this was not feasible anymore. So at some point, people started to use like a green laser, right, to remove the passivation on top of the tracks of interest so they can put a needle there, right? So why not? And this is where the vendors decided to introduce shields, okay? The idea is now, if I take a green laser and I remove the passivation, the only track I see is a track that is not useful to me, and if I cut this track, the chip is killing itself. Okay, so I don't dump anything from a chip which is basically empty. But in the process, attackers needed to access like deeper signals in the stack of layers of the chip. And they were starting to use basically FIBs, right? So that's an FIB. And an FIB is capable of like removing metal, removing oxide, depositing metal, and depositing oxide. So basically you can reroute circuitry, right, at the nanometer scale, which is fun. And because of that, so that's the inside of a FIB, so, okay, nothing too special. But because we were using now FIBs, right, what about shields? You have now a tool where you can take the shield and put it somewhere else, basically. And then you can access the signals you want, right? So, yes, so shields are not, to me, a protection against microprobing. And then we can discuss this after the talk. Yeah, I know some people won't agree. So if you have a shield, alright, so let's say this is all the lines of the shield, and if you cut one, the chip is dead. With the FIB, basically, you can reroute the tracks, right? So now you have an empty space in the shield where you can access the signals that are underneath, right? Looks like this with the FIB. So it's a two local bypass edit, right? And now all of this area is where you can just continue to edge to reach like tracks of interest, which I think is what we did. So before we did this, we had to basically rewire the chip, and then we did this bypass of the shield, put a pad here on the ROM output, another pad like this on the flash output, and basically from this we could now microprobe, so put needles on those pads, and we see that the ROM is starting first, right? So boot ROM. Okay, so that was the information we were looking for. So reading the ROM now is something we want to do. Okay? Still no netlist. So in that situation, we need to find something else. So we know that we don't know. We suppose that the ROM is unclear. So basically, our issue is scrambling, right? And scrambling can be done inside the ROM, and it can be done outside of the ROM. So we tried basically to solve the inside of the ROM thingy by basically taking the pictures of the ROM and making a VHDL model of the ROM itself. So it means reverse engineering the row decoder, the column decoder, the control logic of the ROM, and as we have already the bits, we can have this model. And the idea is, I give you an address, give me the right data, right? So the model looks like this. I mean, like the ROM looks like this if you look closely, right? So you have like banks that generates like word line signals, right? You have multiplexer there, and this is the control logic over there, right? And basically, what we found is like scrambling was everywhere, right? The order of those blocks is not this one; it's a random order. I mean, random, it's not a linear order. Let's say the order of those blocks are also like different. But inside the blocks, the selection of the word lines and the bit lines were also scrambled. So it's a good job of like obfuscating this. So from this, we could build new binaries and try to see if we can see strings or non-node codes, or try to find if we can make sense of the data. We couldn't, right? So that's pretty rare to arrive at this point with a non-encrypted ROM and to have like so much trouble. But one thing we didn't know is the bit order of the address lines and the outputs, because that's inside the digital circuitry that we can find this out, right? So we needed to have the netlist. Okay. So results are a bit annoying, that's for sure. There are still some unknowns, like the address, the base address of the ROM, unknown. Type of processor is unknown. So yeah, we could a bit later we could see that there is a difference between the physical address of the memory and its logical address. But hey, we have the netlist now, so we can get like so much more information. So the netlist is just like a file which is like quite long. If you want to print a part of the netlist, you need to have like a lot of paper, right? And inside the netlist, basically, you have all the digital logic, so you can learn a lot from the netlist itself. So we wanted to confirm that the ROM was not encrypted, but also we wanted to verify all of this, right? Find weaknesses to perform the attack, dump the ROM running code, dump the ROM code, find the order of the data and address lines, and this kind of things, right? So, okay, let's jump in, right? So here, that's schematics that are coming from also one of our tools that converts the netlist to this, and we can search things inside. And what we see is basically the ROM outputs. The first cell that they reach is multiplexer, right? So we can. I mean, that's expected. I expect to have over memories in the design, and we know there's a flash, 2 RAMs, so having multiplexer makes sense. And if you start to trace, what you will find is the RAM, the ROM, and the flash are connected to this multiplexer, right? So that's the memory selection that is just there, okay? But there's 2 other things. This cell and these cells, right? They are XORs, okay? Which tends to indicate that the flash is encrypted, also the RAM. But I don't see XORs for the ROM, right? So I start to assume that this is like clear data bus already. And our hypothesis was that the ROM was not encrypted, so makes sense. Let's just confirm this. Then we went a bit further, right? Because like what's interesting is to know where the registers are, right? Like the combinatorial logic is one thing, but the register. So here are the first stage of registers that are reached by ROM, RAM, and flash, right? So probably that's already part of the instruction register. And there's a funny thing here on this stage, right? You have a control signals that is used by all of these cells, and you can force now the clear data bus to be all ones, right? So we can force an instruction now, which is FF on the chip, with one signal only, one needle on this, and we can use FF as an instruction, right? So we didn't use it yet. But to me, it's a very cool thing, you know, because if FF turns to be an instruction which is like a sequential type, not a branch, you know, then we will be able to do like the instruction skip and start to mess up with the instruction flow itself. So that's a very useful signal here. Bit order, right? So for the bit order, it's pretty easy. Trace the signals until you find a debug chain, right? Or until you find others, right? And that's what we found here. So I don't remember. So that's the bit order, right? So inside the data path, so from the ROM down, at some point you arrive on another, right? So that must be already part of the LU or something. And you see the carry from the other that propagates from less significant bit to most significant bits, right? So now the bit order for the output of the memory is known, okay? And we did the same thing for the address, and here you can really see like the signal just like propagating from less significant bit to most significant bit again, right? So bit order is known for the address. Bit order is known for the data. So if I take the ROM model from before, well, we should have the right binary this time, okay? So I don't know if it's the right binary, but there are still no strings, and there are still no non-opcodes. Okay, but it doesn't stop the attack. You know, we just know that we need to do something more. So, running code. At this stage, we said, okay, let's dump the running code because now we have a binary. We think it's the right one, And if we look the running code of the chip and we compare, we will see where the jumps are, and maybe we can find the base address like this, and elaborate on this thing. And that implies much connections to the chip, right? So local bypass are good, but they take time, half an hour to make the edit, so it seems to be short, but there's a better strategy here. When we look at this shield, it's pretty funny because you have like the big shield here, and on top of the analog block, there's a piece of shield again, right? And I say always like, this is to me like, it's an arrow, you should look here, like some kind of flag that, yes. So basically, yes, we've been looking at this structure that was also covered, right? So you see, it's not that big, right? And we've been putting like a few pictures in Photoshop just to make some kind of like quick reverse engineer of the block. And this is now the shield logic, right? So you have the shield, and it has like several like points where it's basically sent, so evaluated, let's say, and then randomly they choose one of these signals to go to send to the digital logic. So it means that now, if we want to understand the shield, that's inside the netlist of the chip itself, right? And the netlist says this. So this is the beginning of the shield, right? So you have the shield lines that goes in any direction, and this is the what has been sensed by this little block, right? And what do you see here? XOR again, right? So they just compare, right? Which makes sense. But it also means that if I'm here, and I put a logical 0 with a needle or directly connecting this track to ground on the chip, the shield doesn't work anymore, right? It's not there. Whatever happens to the shield, the chip will think it's alright, Okay, so it shows to me that when you hear shields are protection against microprobing, not really, because people that microprobe will use an FIB to access their signal, and because they have an FIB, they can bypass the shield in the first place, okay? Funny part, and I always say, if I find this, I would do a talk, and I'm here today. This cell is a OR, right? And this is interesting, because this signal, you can call it security violation for the shield, right? It arrives on the OR, so it means that the two other inputs for the OR gate here, these are probably security interrupts too. So now, if you go just after this cell, right, and you put this line to VCC, not only the shield is not active anymore, but the two other countermeasures are dead, right? So you don't know what they are, but they will not work, right? They will say maybe that there is a violation, but you just say to the chip, no, don't take this into account, this is useless, it's not for you, bad for the health, and things like this. Alright? So that gives you, I think, an idea of like, what you can do. The cool part was like, this is the track that we want to put to VCC, and the blue track, the white blue track here, that's VCC, right? So the edit itself was just like making a hole, reaching this track, and filling it with like platinum until we reach the VCC track, right? And 3 countermeasures are dead, 2 unknowns, and the shield, right? Okay, so then we probed, alright, so it looks like this. So we use active probes to get like the best signal possible. And then we use Python script to just like work with the data. And here we see one memory output. I don't know which one this is, I can't tell. ROM output 0, alright? And this is the internal clock of the device, right? So that's interesting to get the internal clock, because now you can sample with it, but you can synchronize to it. I mean, that's very useful to have this, right? So we digitized basically the bits we extracted. So 3 bits for the ROM, 1 bit for the flash, and this is running code. No? So we see activity at the beginning, and then it enters some kind of a loop, right? Very fast. And the idea was to compare the binary we think is the correct one to this running code, right? And the longest sequence that we could find of like following up codes was something like 10 codes in a row, which is not so much, if you ask me. I was expecting to have more. And playing with this didn't help so much, alright? So my code is still from an unknown architecture with no strings inside, and I don't know. And so this is where we stopped, or where we are right now, alright? And this all the things I showed to you, that's months of work by the team, right? So that's pretty big. And the next step are not small steps. So when this is done, maybe I do a call for paper for hardware IO again, because it's going to be very interesting. Because now what I think is next step will be to fully simulate the fetching circuitry, right? So like this, it's the memory that's read, and it's the model that is incrementing the address itself and everything. Because what I could foresee, what I can see already in the netlist is like the logical address and the address of the RAM. It's a modified version, right? So they do something in the middle, and I think that's why the binary, I think, is the correct one. Is just not in the proper order still, right? After all we did. So that's going to be first thing, and now we have the code, right? By the way, this chip is you can do linear code extraction attacks on it too. So linear code extraction attacks are invasive, middle, and it's made to dump full contents of memories. So it means that basically we could have full RAM and full flash extracted like this, okay? But still, if I have a binary but I cannot understand it, that's bad. I start to suspect this chip, right, to have a custom instruction set, okay? Which is not very nice. You have a binary and you have no idea of what kind of instruction you need to find inside. So after the fetching circuitry analysis, next step will be to look inside the digital circuitry and to do the instruction decoder, basically rewriting the datasheet. That's what the guys will do. The cloners, if they need to do this, they would do it, right? The market is too big. Yeah? For them, it's a good opportunity. And if we do this, if we rewrite the datasheets, basically, I think the analysis will be completely over. So on their side, they do more, to emulate the product and sell it. But on our side, that's the end of the story, right? So for my conclusion, what can I say? We tried with the talk to show you the process. I mean, like the thinking process. What's an invasive attack? What you do? How hard it is? How long it can take? And I think you can see that it's not an easy thing. Modifying micrometer wide structures with the FIB to probe and have like no more information. It's a tough thing, right? I think shield is a good point to discuss, at some point in real life, and it's also true for some of the other countermeasure. But what you can feel, I hope, if I did a good job this morning, is with sufficient time, the cloners will always succeed to extract what they want, right? So there's not such a thing as a secure chip, right? It's just a question of time, and this is where you can argue that shield is just another layer of protection and that the pirates will lose some time just like figuring this out. Can discuss this. It's an interesting discussion. And last slide, I think, is some kind of history again. I can see that reverse engineering ICs, is increasingly it's getting big, sorry. And as Texplained, for example, we are part of a European project with law enforcement agencies to use this kind of techniques to learn things from like secure encrypted device, right? I think there's still a need to increase the security in ICs, right? And with other methods than the ones that are currently in place. And I think that red teaming the integrated circuit is something that should be done more, right? I know it's expensive, I know it's long, but I think it's very useful to learn, at least for the next chips, right? And there's still like the proper evaluation the methods to be defined, if you ask me, right? Because it's hard to rank like a side channel attack like DPA with the same measure and do also this on invasive attacks, right? I cannot do an invasive attack in 2 weeks. That's beyond my skill, right? So for this, we are also part of another European project, Orshin, which is like basically discussing how we can make like secure hardware in the context of like fully transparent silicon, right? So I give you the netlist this time. And I think that's good. That's where we should go, like the security by design. I show you the netlist. I show you the firmware, and I say you need to do this now to get what you want. And good luck, that's really possible to me. And this being said, that's it. So thank you for your patience. And if you have questions, I'm here.
Thanks, Olivier. Wow. So we have time for a couple questions. Do we have some questions from the audience? We have way too many questions.
Hi. I have one question. Once you got the full netlist, are there any, got the full netlist of the chip essentially? Yeah. Is there anything stopping you from converting that to some hardware description language like VHDL?
That's what we do. The netlist that I'm using here, that's VHDL.
Okay. So you already converted it back to VHDL.
Yes.
Okay.
So on this example, you have like the digital logic is a VHDL block, but the RAM is another one, and they are speaking to each other.
Okay. So then you can simulate the whole.
Yes. So it would be great to simulate the entire chip. First, I think it's slow and complicated, on any computer, and second, I think like it's not possible to get a 100% accurate netlist of the digital circuit because it's big, And if you spend the time to clean it all, right? Okay, that's no. So that's why I'm isolating parts of the circuitry. Fetching, right? That's one thing. Instruction decoder can be another one. So you want to stay small.
Okay, thanks.
Okay, one more question. We have two.
Hi. Thank you for a nice presentation. I have a question regarding the technology node. If you go to the lower technology, do you have any restriction for this whole process?
It's a very tough question. So first of all, I'm looking at secure chips. So tech node 40 nanometer and above, right? So then, can we do it on 5 nanometer TSMC? That's your question in a way, And the answer would be, maybe at Texplained we won't do it because we don't have like projects like this so much, but we did try, to make pictures of those tech. And to be fair, like the chip vendors, they need to have the right machine to do the failure analysis part. So it means that the attacker will be able to do it. It's way more complicated. I don't know, like the layers would be at the end of the day like 50 nanometer thick, right? And you need to be flat inside. It's touchy.
Another question is that this obfuscation field is being evolved with the time. Logic logging is there. Are you aware of these techniques? Could you do so much? If they implement the IC is locked.
The thing is, in this context, for example, they emulate the whole thing. So they would also emulate the blocking, and like this, they don't care. So it's usually not an issue for them because like their goal is really to emulate. So they emulate everything, and this too.
Thank you so much.
Unfortunately, we don't have much time for all other questions. I would suggest everyone to find Olivier in the hall and ask them privately. Thanks, everyone, and we're going to prepare for the next talk. Big round of applause, please.
Thank you.